Greetings, science family. Today we are going to be reviewing how to do Lewis dot diagrams for our molecular model kit lab. Let's start with water. For water we have H2O, which means we have 2 hydrogens and 1 oxygen. If we want to do the Lewis dot diagram for it, we have to make sure we count up how many valence electrons. So since hydrogen is in group 1, hydrogen has 1 valence electron. Since oxygen is in group 16, it has 6 valence electrons. So that means we have a total of 8 valence electrons we need to use in order to create water's dot diagram. Well, oxygen is by itself, so I'm going to put that in the middle. I'm going to put a hydrogen on each side. Now, if we look, we have 8 total electrons that we can use. We know that we have to have a single bond to each hydrogen to the oxygen because hydrogens only want 2 to be happy. So that means we need to give at least 4 more to get oxygen with 8. And when we finally do our dot diagram and double check, you'll see that oxygen has 8 around it and each hydrogen is touching 2, which makes them stable, and we only used 8 electrons. So this must be a proper dot diagram for it. Let's move on to ethyne. Ethyne has 2 carbons and 2 hydrogens. Now, if we look at carbon on the periodic table, it's in group 14. So carbon has 4 valence electrons. Each hydrogen has 1. When we add that up, 4 plus 4 is 8 plus 2. We have a total of 10 electrons. All right. We know that hydrogens have to be on the end because they can only have single bonds. So I'm going to put the 2 carbons in the center. Now, as we know, let me make this a little bit bigger here. We are going to only need 2 electrons to bond the hydrogens together. All right, now if we look, the carbons in the center, they at least have to be bonded together. Now already I'm using 6 electrons and I only have 10 that I can use. But if you look at the carbons, they each are only touching 4. So that's an issue. I think I'm gonna need more than just a single bond in the middle. So let me try 4 in there. If I do that, now each carbon is touching 6 electrons, 2, 4, 6, but I've used 2, 4, 6, 8. I've only used 8 electrons, I only have 2 more. So now I only have 2 more electrons that I can use, but I need each carbon to have 8. The only way to do that is to share again. So I'm gonna do a triple bond in between the 2 carbons in order for the carbons to be sharing 6 between them and having 8 total. But that's what ends up being our dot diagram, all right? That is a triple bond. By the way, if you would want to draw that a little bit different, you could draw that as carbon, 3 dashes, and a single dash to show that that's a triple bond between the 2 carbons. All right, let's go to the next one. What's our next one? Methane. CH4. So we've got 4 hydrogens, right? Carbon is group 14, so it has 4 valence electrons. Each hydrogen has 1 valence electron because it's from group 1. Total of 8 valence electrons. Since we have 8, for electrons, let's start putting this together. Carbon is the oddball, it's all by itself. So I'm going to put carbon in the middle. With 4 hydrogens, I'm going to put a hydrogen on each side of it, so a little north, south, east, west alignment. Now that I have that, I do have to be concerned with how they bond together. So between each carbon and hydrogen, I need to at least put a pair of electrons to get that single bond. When I did that, each hydrogen is now happy with 2 electrons, and the carbon is happy with 8. And we used 8 electrons, so we solved the puzzle. We're actually good. 8 electrons, everybody's stable and happy. Each hydrogen has 2 and carbon has 8. So that's a good dot diagram. On to our next one. I erased a little bit from the previous to make room, but we've got chlorine. Chlorine is 2 chlorines actually bonded together. Now, chlorine's in group 17, so it has 7 valence electrons. And 7 plus 7 gives you 14. So that means we're dealing with 14 electrons. So if we do that together, let's see. I'm going to use 14 total electrons. That's a lot. So I'm thinking I'm going to start with a single bond and see how that goes. So there's the single bond, and then I'm going to put lone pairs, 6 on each chlorine of lone pairs, so that they have 8 each. Let's count up. That's 2, 4, 6, 8, 10, 12, 14. Perfect. With a single bond of chlorine and 3 lone pairs on each, you use 14 electrons and the chlorines are stable and happy. So this was a single bond for the chlorines. Perfect. Let's take a look at the next one. Ammonia. Ammonia is NH4. So there's 4 hydrogens for every 1 nitrogen. If I look on the periodic table, nitrogen is in group 15, so it has 5 valence electrons. Each hydrogen has 1, so when you add all that up, 1, 2, 3, 4 plus 5 is 9. You have 9 valence electrons. But this has a positive 1 charge. And if you have a positive 1 charge, that means you have to take away 1 electron. So we really have 8 valence electrons to work with. Ooh, we like 8 because when there's a center atom, we can draw 8 electrons around it, and usually that works out good. So let's see. If nitrogen is in the middle because it's the oddball loner, and there's 4 hydrogens, I'm going to surround it north, south, east, west style with 4. I'm then going to draw in my single bonds because each hydrogen can only have a single bond. And look what happens. We used 8 electrons total, which we had to. Nitrogen's happy because it's touching 8, so it's full. And each hydrogen's happy because it has a single bond or a pair of electrons being shared. Voila, we have our dot diagram for that specific one. Perfect. Let's look at the next one, hydrogen fluoride or hydrofluoric acid. If we look, we've got a hydrogen and a fluorine. Hydrogen's in group 1, so it has 1 valence electron. Fluorine is in group 17, so it has 7 valence electrons for a total of 8. We love when we have 8 valence electrons. So let's do the hydrogen and the fluorine together, and let's think about it. There can only be a single bond between the hydrogen and fluorine because hydrogen can only hold 2 electrons. So the rest of the electrons must be on fluorine, and that makes sense. 3 lone pairs will give fluorine a total of 8 that it's feeling, and that'll make it now balanced out. And we only used 8 valence electrons, so we're good. If we move on to the next one, you have hydrogen. Hydrogen only has 1. Hydrogen only has 1, so we're only using 2 electrons. Ooh, I like this. This should be straightforward. If each hydrogen only can hold 2 electrons and we only have 2 electrons available, this must be our dot diagram, a single bond to hydrogen. Remember, when you draw that too, another way to draw it is with a single dash, right? Those 2 dots in between 2 elements is like a single dash. Again, up here too, we could have drawn this ammonia like that, right? And technically, since this has a charge, remember, we are supposed to put that in brackets, technically, to say that it has a +1 charge. That was important and something I should have definitely mentioned. Starting on the next page, dichloromethane. We've got a carbon, hydrogen, hydrogen, and 2 chlorines. Carbon's a group 14, so it has 4 valence electrons. Each hydrogen is in group 1, so it has 1 valence electron. And chlorine is in group 17, so it has 7 valence electrons. Add all that up, 7 and 7 is 14, plus 4 is 18, plus 2 is 20. So you have a total of 20 valence electrons, all right? So how do we do this? Well, we've got, carbon, and then there's 4 other things, 1, 2, 3, 4. Carbon likes to be surrounded by 4 things, so let's try that. Let's do carbon, hydrogen, chlorine, and hydrogen again. Let me erase that really quick and put a hydrogen there. All right, now that I have that, let's think about it. I need to use 20 electrons. I know each hydrogen is going to have a single bond, so my hydrogens are good. I know what the chlorines are going to at least have to have a single bond to connect to the carbon. So my carbon's happy and my hydrogen's happy, and I've used 8 only. That leaves me 12 electrons left. But if you think about it, each chlorine only has 2. It needs 6 more. So 6 plus 6 is 12. So I'm guessing just putting lone pairs on these chlorines is going to be enough. And it is. Each chlorine now has 8, the carbon has 8, and each hydrogen has 2. And I use 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. Perfect. So this is all single bonded with carbon in the center. All right, I'm glad that one worked out. Let's look at nitrogen. 2 nitrogens, each nitrogen is in group 15, so they have 5 valence electrons. All right, if nitrogen, let's get a different color for that. If we do a single bond for each of them, we have to use a total of 10 electrons, right? So if I did a lone pair on each of them to give them 8, I think I'd use too many. 2, 4, 6, 8, 10, 12, 14. Yeah, that's way too many. So something else has got to change. So let's see. If we did a single bond, there'd be too many. So let's do a double bond. If we did a double bond, you'd have to have 4 on each nitrogen to give them 8. That would be 2, 4, 6, 8, 10, 12. Ooh, still too much. So it can't be a double bond, must be a triple bond. If I put a triple bond there, now each nitrogen has 6 in the middle with 2 on just the nitrogens. So that's 8 for each of them, and I use 2, 4, 6, 8, 10 total. So when I have my nitrogen, it's actually a triple bond. And you can put your dots on the outside if you like. But there you go. There's our dot diagram for nitrogen. Let's move down then. Carbon dioxide. CO2, 1 carbon, 2 oxygens. Carbon is group 14, so it has 4 valence electrons. On the periodic table, oxygen is group 16, so it has 6 valence electrons for a total of 16 we can use. Carbon is the loner, so I'm going to put carbon in the middle, oxygen on each side. Now that I have that, I've got to start figuring out how can I get everybody stable with 8, but only use 16. So if I do a single bond to each, now we're all connected. Let's see, if I do, everybody just gets their lone pairs. Let's see how many total that is if we just did a single bond. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Whoa, way too many. We're using 20 electrons instead of 16. So the single bonded to everybody was not the right answer. Okay, that's fine. Let's try it another way then. Let's try, since I had too many, let me try a double bond on each of them. By doing the double bond, notice carbon is now full. It has 8 electrons. Now each oxygen has 4, so it's going to need another 4 to get 8. So let's try that one. If it doesn't work, that's okay. We'll try a different one, maybe 1 single, 1 double. But now that everybody is touching 8 electrons, let me see if I use 16. 2, 4, 6, 8, 10, 12, 14, 16. I did. I used 16 electrons, so we're good there, and everyone's happy with 8. So this must be a valid dot diagram. A way you could write that, of course, instead of putting 4 dots in between the carbon and oxygens, is 2 dashes for a double bond. And then you could put your dots on top and on the bottom as well. So let's now move methanol up so we can do our last few problems, and we'll be good to go. So methanol, CH3OH, CH3, so 3 hydrogens, an oxygen, and another hydrogen. Wow. Well, first of all the hydrogens have 1. Carbon is in group 14, so carbon has 4 valence electrons. Oxygen, group 16, has 6 valence electrons. So when I add all that up, it looks like 14 electrons total. Now, carbon loves being in the middle, surrounded by 4 things. It can only be surrounded by 4 things because 2 times 4 is 8, so carbon is full. So it looks like it says CH3. So let me not get ahead of myself. Let me put my 3 hydrogens on it. CH3, that's how it's written. And then it said OH. So I wonder if the oxygen is connected to the carbon, and then the hydrogen is going to be connected to the oxygen. So let's try that out first. Let's do single bonds to everything. So hydrogen's connected to the carbons, and then the oxygen's connected to the carbon. The hydrogen's connected to the oxygen over here. The only one that's not stable, because look at carbon. Carbon's now surrounded by 8 electrons, right? But oxygen only has 4, so let's give it 4 as well. When I do that, everybody's single bonded, And everyone, let's see, each hydrogen has 2, carbon has 8, oxygen has 8, and 2, 4, 6, 8, 10, 12, 14. Good. We used 14 valence electrons, so we're good. We ended up with a nice dot diagram. If I draw that out with my single bonds as dashes instead of dots, which you don't have to, but some of you prefer that, I think it'd look more like this, and then you'd have 2 lone pairs on the oxygen. All right. Nice job. Well done. Either one of those drawings is acceptable, but they shouldn't be in the second column. Decide which one you want. If we look at the very next one here, hydrogen peroxide, H2O2. 2 hydrogens, 2 oxygens. Each hydrogen is in group 1, so it has 1 valence electron. Oxygens are group 16, so they each have 6. 6 and 6 is 12, plus 2 is 14. So yet again, we've got 14. Now remember, hydrogens are always on the ends, so that means oxygens must be in the middle. I'm going to make this symmetrical. I'm going to put an H on both sides. If I take that and move forward, I'm going to at least single bond the hydrogens to the oxygens, and the hydrogens are happy. And I'll single bond the oxygens. Now by doing that, oxygens are not happy yet. They only are each touching 4. They need to touch 8. And we've only used 6 of the 14 electrons. So we have a lot of electrons left. So I'm going to start by using single bond. See what that does. Everybody's now happy. Each oxygen has 8. And 2, 4, 6, 8, 10, 12, 14 electrons were used. So I'm feeling pretty good that that's the dot diagram for it. Feel free, if you'd rather draw it the other way with the dashes instead, you can do that. Just don't forget to keep your lone pairs of electrons on the top and bottom of each oxygen. Moving to the next one, speaking of oxygen, we have pure oxygen, which is O2. It's a diatomic molecule, meaning that oxygen bonds with itself. Oxygen's group 16, so there's 6 valence electrons on each oxygen for a total of 12. Only oxygen can bind to itself since there's only oxygens there. So we got to figure out how to solve this problem so that we use only 12 electrons. If we give everybody their lone pairs in a single bond, I use 2, 4, 6, 8, 10, 12, 14. I use 2 too many, so that's not going to work. Okay, so if a single bond didn't work because I had too many, let me try a double bond. By having a double bond, now each oxygen has 4, so they only need 4 more. Wow. Let's see if that works. 2, 4, 6, 8 for each oxygen, perfect. And 2, 4, 6, 8, 10, 12 electrons being used in total. So that is a good dot diagram. I think that's good. All right. Let's scooch this one up. Hydrogen monosulfide, last one. Let's get it done. 2 hydrogens and 1 sulfur. Each hydrogen's from group 1, so it has 1 valence electron. Sulfur is from group 16, so it has 6 valence electrons for a total of 8. We love 8. Sulfur has to be in the middle. It's the oddball. Hydrogens have to be on the end because hydrogens can only make single bonds. Once we do that, sulfur has 4, so it has to have another 4, and it works out perfectly. You can't use them in bonds because the hydrogens are full, so sulfur just has 8 around it for a total of 8. So your dot diagram works out great. Again, if you wanted to do it with dashes, you would just do the dashes instead of the 2 electrons for the bonds, and you'd still leave the lone pairs. Oxygen as well, it's a double bond, so you'd be 2 dashes, and then you'd still have to put your lone pairs on there. All right, science fam, we got through our lab and drawing our dot diagrams. Perfect. Let's get that done, and we'll move next to building the model kits so we can draw the ball and stick model, which means we'll actually draw the proper shapes. Take care, science fam.